OK, so visually, let's say that instead of just executing a single instruction, I'm now going to start pushing a series of instructions through my pipeline. So here we have a diagram showing what the CPU might do with 4 instructions. So down here is basically time. So we call the execution of each phase in this pipeline a clock cycle. And that just means the CPU is going to do one thing. So I'm going to fetch something, I'm going to decode something, I'm going to execute, and then I'm going to write. So we can see here that as time goes on, it takes me 4 seconds, or 4 steps, to execute this instruction. Now once this instruction is done, I move on to the next instruction. And it's going to take 4 steps to execute that instruction. Now I'm going to move on to the next instruction and kind of keep going until everything is through our assembly line. So what's the problem with this? Right? What are some potential things we could do better given this diagram? So it seems to me like we have a lot of wasted space and time. So how could we improve this? Anyone have any ideas? Yeah, exactly. So now we can start introducing something called parallelism. We can start to make things happen at the same time. So when I say that I execute things in parallel, it means just that. I have 2 separate tasks, and I'm going to execute them concurrently. So effectively, the CPU can be doing 2 things at once. So for example, if we look at our assembly line, we can see here that we have these different stations, or different kind of machines, dedicated to the different parts of this process of assembling a car. So if we just had one car go through this assembly line at a time, that would be kind of wasteful, right? The first machine would do something, then that first machine is going to sit and it's going to wait until another car comes through, and that's kind of a waste of time. So as this picture shows, we're actually going to be pushing multiple cars through this assembly line. This first machine is going to do its job, then the car is going to move on, and a new one's going to come in right away. So the machine's not waiting for that first car to be completely assembled before it moves on to the second one. So we can actually do the same exact thing inside of our CPU. So before, down the bottom, we had 16 steps down here. Now we only have 7. And see what we've done? Instead of waiting for this entire instruction to be completed, so we didn't wait for all 4 of these steps to be done, what we did is we said, OK, this first instruction is coming in. That means our fetch machine on our assembly line is going to start doing its job. So now we're going to say, OK, the fetch machine's done. It's time for the decode machine to start working on this same instruction. So now, rather than waiting for that to complete, we said, OK, well, if the fetch machine's done, in this second column here, now we have 2 things going on at once. The fetch machine is working on the next instruction, while the decode machine, or the decode part of the CPU, is decoding that original instruction. So now if we move on again, we can now see we're doing 3 things at once. And again, we're never overlapping. The fetch part of the CPU is only ever doing one thing at once. The decode part is ever only doing one thing at once. But because we can break this down a little bit and say that we don't need to wait for this entire instruction to complete before we can fetch a new one, we can actually do much, much better in terms of efficiency. So now it took less than half the amount of time that it did before. We're executing these same 4 instructions. The only change we made is we're allowing the CPU to effectively do more than one thing at once. So because we have these defined phases, and they're each executed by different parts of the CPU, what we can do is we can start parallelizing. We can say, OK, I want all of these different parts to be running at the same time. So does that make sense? Any questions on that concept? OK. So by the way, this happens to be called a superscalar architecture. So there's the fancy word of the day today. Last week's was CMOS. And so this is just the name of this architecture that says I want to start executing things at the same time, so that I don't have the fetch phase just kind of sitting there dormant while other things are going on. So that might be a little abstract. And so let's actually motivate this a little bit with an actual example. So while you're buying computers, you may have seen something called a multi-core processor. And a multi-core processor is simply a CPU that has multiple CPUs. So a dual-core processor, for example, has the equivalent of these 2 separate CPUs. These 2 separate processors can execute things at the same exact time. So that means that if you're running 2 programs at once, like you're checking your email while you're browsing the web, that means one CPU can handle all of the instructions related to checking your email, and the other CPU can handle all of the instructions related to browsing the web. And so now this is much more efficient. We don't have to have just this one processor handling both of those tasks. We can split it up to make things a lot more efficient. So let's have a real-world problem here. So let's say that it's Halloween, and you just went out trick-or-treating, and you have a giant bag of candy. And what you want to do is you want to figure out how good at trick-or-treating you were. And to do that, you want to count up this entire bag of candy. So can I have 4 volunteers? That would be OK appearing on camera. 1, don't have to talk or anything. 2, 2 more? Yeah, 3. 1 more, it won't be embarrassing. RJ, all right? So up here, yeah, now you're excited. So up here, we have a table. And I have here this big bag of candy. So you all want to come around here? So I have a giant bag of candy here on the table. Actually, have more candy if we need it. OK, and so our job is we want to figure out how good at trick-or-treating we just were. So let's say that I don't have any friends with me. And instead, it's just me and this giant bag of candy, which actually isn't a bad day. So the process of me trying to figure out how much candy I have might look something like this. I have this big pile. I'm going to say I have 0 pieces of candy. For each of these candy pieces in the pile, I'm going to say I have 1 more piece of candy. And I'm going to remember that, all right, I counted that Twix bar. I'm not going to count that again. I'm going to keep going until I'm done. So that's going to take a while, right? If I have 100 pieces of candy, it's going to take me 100 steps to complete that process. And that's not a bad problem to have because I have 100 pieces of candy. But let's say that we can do better. So the first thing that at least I might do is try to say, I want to recruit some friends to help me out with this process. I have this big task. I don't want to do it by myself. So the first thing I'm going to do is I'm going to find 4 friends. I've completed that step. So now step 2 says that I want to divide this big pile of candy among my 4 friends. I probably want to do this evenly so that it's, RJ doesn't get all the candy. So let's just divide up this pile among the 4 of you. So you each have your own smaller pile of candy. RJ hoarded all the crackle bars, but that was totally expected. So now I have my 4 friends, and now they can count their candy at the same time. Right? There's nothing to stop RJ from, RJ doesn't have to wait for everyone else around him to finish counting candy. He can just start counting. So you don't actually have to count your candy, so just kind of make up a number in your head. So now that's it, right? Suddenly I have all my candy, and I've done it 4 times as fast, right? Because I had 4 people. Anyone disagree? Yeah.
Might have done it more than 4 times as fast.
Sure, so I might have done it even more 4 times as fast. But what do I have now? How many answers to the question, how much candy do I have? How many different answers do I have? If RJ has an answer, yeah, so right now I have 4 separate answers, none of which are right. Right? I suddenly have all these 4 smaller numbers, and I need to figure out how to go from 4 smaller numbers to this big original total. So we're actually not quite done solving this problem. So we've counted all the candy 4 times as fast, or maybe more, depending on how we divided things up, or who counts faster. But now we need to somehow figure out how to go from 4 things to 1 big total. So here's one way I might want to do that. So I might want to say, OK, it's me, it's all my candy. I'm going to ask everyone what their total was. So what's your name first?
Chris.
Chris. So what was your total, Chris?
15.
15. And what's your name?
Carrie.
Carrie, what's your total?
22.
15, 22 is 37? Yeah?
Sure.
OK. All right, what was your total?
18.
37 is 55. And what's your name?
Eric.
Eric, and what was your total?
15.
15. So that gives us 70 pieces of candy if I added right. If I didn't, then we now have 70 pieces of candy either way. So how long did it take me to add up all of those totals? It took me 1, 2, 3, 4 steps. So that means now we're a little bit faster, right? Because we cut our original problem into 4. Everyone counted individually. And now I added things up, and I only needed 4 steps to add everything up instead of 1 step for each piece of candy. So that's OK. But let's say I want to do even better. So I want to speed this up even more. So what I do is I say, rather than 4 friends, I get more friends. And let's say that I have so many friends, which I don't, but that I can get so many friends that each friend gets a single piece of candy. Right? Why might I want to do that? Because that means that each of these friends has as little work to do as possible. Right? It's going to mean that they can count their pile of candy, which is just one Twix bar, really, really fast. And that's great, right? Because I can't do better than that. But now how long does it take me to get from those small totals to a big total? How many steps is it going to take? Exactly. So now it's going to take 1 step per piece of candy. So I'm actually doing worse, despite my immense popularity, because it's going to take 1 step for everyone to count, and it's going to take me another step for each original piece of candy. So I was better off just doing things all by myself. So seems like we can improve on this a little bit. So let's try a modified way of adding everyone's totals together. So as we said, this was not actually that much faster. So let's try this step instead. So this is going to look a little weird, but let's see what happens. So what I want you to do is each of you to pair off, and I want you to add your totals together, which is going to give you some new total. And so if we have Chris and Carrie, add your totals together, and we have RJ and Eric, add your totals together. So ready? We can do this at the same time. So go ahead and kind of come up with one number between you two.
So we have 37.
OK, so what's the number over here?
37.
37?
33.
37 and 33. So they just added those together in parallel. So now I went from 4 small sums to 2 small sums. They're both still wrong, but it kind of feels like I'm on the right track. So the next step here is that we can say one friend needs to remember that total, and the other friend doesn't need to do anything anymore. So now let's do this process again. So we have these 2 totals, and so one of you, Chris or Carrie, can talk to either one of Eric and RJ and add your totals together. So what do we get?
33 gives us 70.
So now we have 70. So now how long did that take? So we broke it up into 4 small problems. We solved them all at the same time. And now, rather than taking 1, 2, 3, 4 steps to come up with a big total, it only took us 2. So this is actually much faster. So this is just simply a different way of solving this same problem. So it seemed like before, the crux of the issue with my asking everyone individually what their total was is that I'm not really doing things in parallel anymore. It's just me doing things at the same time. And as I'm asking RJ, I'm kind of wasting Chris's time because he's just standing there waiting. So what I really want to do is I want to try to involve everyone as much as I possibly can. And this is kind of one way of taking this problem and solving it in parallel. So thank you very much to our volunteers. Feel free to take as much candy as you want. And at the break, everyone else can take as much candy as you want, despite your lack of volunteerism, but that's OK. So thank you very much. So any questions on how that worked, or how we went from this large problem of counting candy individually, and suddenly we did it much faster, which means we can start eating it much faster, which makes RJ really happy. Any questions?